Good morning, guys, and welcome to Physics 252. Today is Tuesday, so this is the Tuesday session. Just from the get-go, so that guys are aware of this, on Tuesday, a week from today, on the 12th, there is no class. Are you guys aware of that or not?
Yes.
Okay, very good. Because of the in-service in college, so the campus basically is closed, so we cannot also do an online session because I myself will attend some meetings on that day. So the 12th is no class. The 14th is actually where when our exam is. So Thursday next week, we will have our exam too. Just also to go on the mechanics of things, we're scheduled for the final on the 19th of May. This is the second day of the finals week, basically. It starts on the 18th. So our final is on that day. And we should be done. I'm hoping that we should be done by all the materials by then. So we should be in good shape in terms of everything. I also unlocked the homework assignment for chapter 40, and it's combined with chapter 41. So they are actually on Pearson. So hopefully, guys, you will have a chance to look at them before the exam, which is Thursday, not this Thursday, Thursday of next week. So you have ample of time to look at them and start working on your assignments, because those things are also part of the exam. So this is in terms of the basically the overall business. We're done with chapter 41 in terms of concepts. We still have to do some applications. I'm going to emphasize on the fine structure at this point. And we're going to introduce actually also stuff from chapter 42, okay? Chapter 42, if you look at the title, it's divided into two components. One of them is molecules, and the second one is basically condensed matter. So this is the aggregates of atoms. When they start to assemble together, they form one or the other two structure, namely a crystalline structure for solids, or even or molecules in general, which is a small number of atoms getting together to form molecules. So this is basically the entire idea with the chapter 42, okay? So we've explored a lot of points up to this point. Chapter 38 and 39 are really set up. The chapter 40 is also set up in a sense that it's getting you ready for the real thing, which is chapter 41. Chapter 41 is quantum mechanics for atoms, basically. And that chapter really leads to chapter 42, which is really going to be at hand. Before I do start on this thing, let me grab the book. And any questions related to the business in general, about the dates and things like that? No? Okay. So I gave you a bunch of problems to look at, and one of them, and I made a big emphasis on from chapter 41, and that would be problem 53, okay? And problem 53 is related to an example that I didn't do in class, but I'm hoping that you guys go through it thoroughly. And that example is example 41.8 from the book. And that example is on page 1383, okay? So I'm hoping that you guys go through that example in detail and understand, and I'm going to refer to that example in solving this problem for 53. So that you guys see how these things work, because you really need to have a handle over these things. I mean, it may sound complicated when you read it at first, but then when you start doing it, you see that your way through it, and it becomes not that hard actually. Okay, so let me visit example 41.8, and then we're going to delve into problem 53. And problem 53 is actually much easier when you have a bunch of data, and it's all based on one formula, really. It's a good idea to get Excel going with you, because at some point you're going to be ordering things, and Excel is suitable for that. It can order things for you. And Excel actually is useful also for plug in the number and basically change one number, and that's it. And the whole thing changes with it at once. or copy and paste formulas. So don't hesitate to use Excel in your exam and things like that, okay? So it's really a handy tool for doing calculations. If you have other calculators, that's also suitable too, that as long as they can do what they do, what this does also. The thing that I have in mind is actually GeoGebra. GeoGebra is a very powerful also calculator, and it's actually graphing tool also, so it's really a nice tool also to be able to do things with it. Anyway, so let me look at the example. Let me share the screen first of all. Let me find it and share. Okay. So right now we're still talking about chapter 41 actually. And so we're doing 41.8, which is an example from the book, okay? And we're going to take that example and solve problem 53. Okay, so what they said in this example in here is that for an electron with orbital quantum number L equals to 0, the angular momentum is due to spin, because at that point mz is equal to 0, so there is no component for the angular momentum in that direction or any other direction, because L itself is 0. So that means that the angular momentum itself is square root of L times L plus 1 times h bar, and this is 0 because L itself is 0. So there is no angular momentum due to the orbital motion. Okay, so so the only thing that is we're left with is the spin. So J, remember, is equal to L plus or minus 1/2 under absolute value, and that is only because this one is 0. That is only 1/2. So that is the value of J that you're going to plug in the formula for the fine structure. Okay, and the fine structure formula, if you guys remember, has two components in it: the one that depends on N by itself and the one that depends on N and J. So it's negative 13.6. We're going to be using the electron volt all along. So I'm going to use, we're using, actually the formula has a 4-digit 4 sig figs. So we're going to be retaining up to 4 sig figs. You will notice, so divided by N squared, you will notice that the corrections in here are very small. And that is because alpha itself is small and divided furthermore by N squared. So alpha itself, if you guys remember, it's 1/137.04. So when you square this number, it's going to be ridiculously more, 10 to the negative 4. So in this case, if you're going to make corrections in here, there are going to be several decimal points in here. Okay, so you have to be aware of these points in here. Times, of course, N over J plus 1/2 minus 3/4, and the whole thing is multiplied by negative 13.6 over N squared. So the energy levels that Mr. Bohr has found with his simplistic idea, and then also when we solve the hydrogen, the Schrödinger's equation for the hydrogen potential, basically for the potential for the hydrogen atom, it gave us just this term, negative 13.6 over N squared, where N is an integer going from 1 to whatever number you like. 1, 2, 3, and so on and so forth. Okay. Now, because of the spin-orbit coupling, namely the fact that the electron has a spin, which is not part of quantum mechanics, by the way, the original version of it, so it had to be corrected. Because of that spin and how it couples with the angular momentum, now we have a term that depends on J. Okay, and J depends on two parameters, depends on the angular momentum itself and the spin. So that is where the spin orbit coupling coming from. So the degeneracy that existed before, namely the fact that the energy levels have only N in them, did not depend on L or M. Now all of a sudden they depend on L itself, indirectly of course through J, okay, which is the total angular momentum in this case, which is the sum of the orbital angular momentum L. So I always call this one angular momentum, but I mean the orbital angular momentum, and this one is due to the spin. So the coupling of these two, the spin orbit coupling, that leads to corrections, albeit minute correction, hence the name fine structure, okay? So the energy levels that existed before are corrected. It's not negative 13.6 divided by n squared, but added to them this tiny number in here, okay? So this is basically the idea that we have. And we have to basically, so what we have in this problem, we have L equals to 0. That means J is equal to 1/2, okay? So this is one level. So this is the L equals to 0, which is S, by the way. L equals to 0 is the, from the SPDF configuration, is the S level. It doesn't matter which n we are talking about. And then, so for an electron, the quantum, the angular momentum due to a spin, only one possible value of the angular momentum. And for J equals to 1/2, so which is J, if L is equal to 1, two possible values. Obviously, if L is equal to 1, we have two potentials in here. Namely, J is equal to the absolute value of 1 plus or minus 1/2. When it's plus, is actually equal to 3/2. When it's minus, is exactly, when it's with a minus sign, is going to be 1 minus 1/2, which is exactly 1/2. So in this case, for P, you have two values. So for L equals to 1, which is P, you have two potential values in here, namely 1/2 for J or 3/2 for J, one of the two, okay? Obviously, this number in here will be added 1/2 plus 1/2, which is 1, or 3/2 plus 1/2, which is 2, okay? So in either case, you're going to add that number. Obviously, that depends also what we're talking about, what n we're talking about, because it's important to plug in the n value also. Okay. If two values, so there we have them. A, find the energy level of the state of the electron of hydrogen atom from n equals to 2, L equals to 1, J equals to 3/2. So n equals to 2, L equals to 1, and J equals to 3/2. That's one level. And then n equals to 2, L equals to 1, and J is 1/2. Okay, this is the P level. This is the second energy level. So it's 2. And now, because of the coupling, we're going to represent with capital P, not lowercase p. And we have the index in here indicating the value of J. So the same thing in here. This is 2 capital P because both of them have L equals to 1, but this is the index of 1/2, namely the value of J, okay? So find this energy. So when we find this energy, all we're really doing in here is changing this value. So n is the same value, n is 2. So I'll have a 2 squared in here, and I have a 2 squared in here, and I will have a 2 in here. But J changes from 3/2 and 1/2. For this one, I will have a 3/2. Because it's actually in the denominator, I will be dividing by 2. So this number should be in magnitude, because of the sign in here, should be smaller than this number, okay? So in other words, the shift from the energy level. Here is E sub n. This is the value that we found from the Bohr's model, or for the original value from the quantum mechanics before the coupling. Now we're going to shift that value by an amount for En 3/2, this value. And we're going to shift it by different amount for En equals to 1/2. Okay, for J equals to 1/2. The reason why I shifted them down, both of them are actually negative. I mean, if it's positive, you have to shift them up, that's all. Okay. But I'm suspecting in here the 1/2 will have a higher shift than the 3/2. And of course, it's all in the calculations. You really have to calculate things in here to see exactly which one shifts. Obviously, for n equals to 2, both of them are E2. So this should be 2, this should be 2, and this should be 2. Okay. You guys see that this is doable now? You can calculate these things?
Yes.
So as long as you calculate them, see which number is bigger, then that gives you the shift basically from the value that you will have, which is negative 13.6 divided by n squared, which is 13.6 divided by 4. And that should be, I have Excel open in here. I opened it earlier. So 13.6, no, I have to put the equal sign, otherwise Excel doesn't calculate. 13.6 divided by 4, and this is 3.4. So this is 3.4 electron volt. Actually, probably I should have 3 sig figs in here, 4 sig figs all together, because this is exactly this value. Now I need to find those tiny shifts for the energy levels. So those are the coupling shifts. So I'm going to call them EC for 3/2 for the same energy level in here, or probably delta. So it's actually this number in here, negative 13.6 divided by n squared times n squared, that's n to the power 4, times alpha squared times n over j plus 1/2 minus 3/4. Okay, I have to plug in the numbers. Now it's negative 13.6 divided by 2 to the power 4 times alpha. Alpha is 137.04 squared. I know there is another number that involves a power in here, but if I do that, I don't remember that. I always remember it as 137, 1 over 137. This is a tiny number. Times 2 over 3/2 plus 1/2 minus 3/4. Because of this 3/4, don't do the divisions, because at some point you're going to get into the common denominator. So it's negative 13.6 divided by 16. 4 times 4 is 16 times 137.04 squared. And then in here, so it's going to be 3/2 plus 1/2, that's 2. When you multiply both of them by 2, so it's going to be 4 over 4, because it's 1 actually. 2 over 2 is 1, so it's 4 over 4, minus 3 over 4. The point being in here is try to pay attention to this sign, okay? That's what determines the shift, because this is positive number, which is a quarter. Then in this case, it's going to be a positive number, so it's going to be negative 13.6 divided by 4 times 4, which is, 4 times 16, which is 64, times 137.04 squared. Okay, so this is how much shift for the 3/2. Okay, the same thing for 1/2 is going to be negative, again, 113.6 divided by the same number, which is 16, times 137.04. So the only thing that really changes in here is this ratio, 2 over 1/2 plus 1/2, which is 1, because j is 1/2, minus 3/4. Again, the common denominator in here is 4, so it's going to be 8 minus 3, which is 5, times the same number. So it shifts by 5 times negative 13.6 divided by times 5 divided by 4, which is 64. So it's going to be shifted way below. It's still negative number, okay, by the way, which is important. So it's going to shift by 5 times this much. So the closest one to the energy level in here is going to be the 3/2, and the other one is going to shift so much in here, relatively speaking. It's 5 times squared in here. Lambda squared. Okay, it's going to shift by 5 times. But if you calculate this number, it's a very tiny number. Okay, it's a very tiny correction. And the reason why you would want to separate it from the original value is because of the sig figs. Because if you plug in a calculator and tell it to retain only 4 digits, you probably are not going to see any difference between the two. They're going to be identical. Okay. So you have to pay attention to this little detail. Sometimes it's in an exam, you see that there is no shift. I mean, you plug in the whole thing. Which one? This whole thing in a calculator or Excel, and it tells you, and you tell it to give me only the 4 sig figs. So it's going to retain only the 13.6 divided by n squared, wherever that value is, times 1, of course, because this number is a small number. Hey guys, do you guys understand the point in here?
Yes.
Yeah.
Okay, very good. So calculate the shifts by themselves. Because at the end, that really what matters, the shifts in this case, if you're going to see a broadening on the thin lines. Otherwise, if you have a low resolution diffraction grading, you're not going to see this difference because it's so small. But if at high resolution, you're going to see a shift in there. And that has to do with this numbers that I'm talking about. Even 5 times is still a small number. Okay. So, by the way, all of these calculations are in electron volts, okay? They are not in joules. So all of this energy is because of the 13.6, they're in electron volts. So if you really want to have them in joules, you have to convert into, by multiplying by with 1.602 times 10 to the negative 19 to get how many joules we're talking about, okay, if you really need the SI. But everything in here is calculated in electron volts. So all of these energies are in EVs. So if at some point you need a lambda, which is needed, you probably have to make that conversion, okay? So that's important.
So, Professor, could you scroll back up to the function that we used originally?
This is the one.
Yeah, that was the one there. So the only thing I'm confused on is what happened to the factor of the negative 13.6 divided by 4? Did we take that into account in the E sub C's for both of those, or?
Okay. Okay, this is exactly my point in here. Okay, this is that point value. It's negative 3.4000. Okay,
Right.
I'm not calculating that. I'm not calculating this value. I'm just focused on the shift only, on the due to the coupling.
Oh, okay.
Okay, because if I include that in my calculation, both these values, my calculator will give me this very same value. So I would not see if I am taking the precision to that level. I'm not going to see a shift. So I'm only focused on this term only by itself, times, of course, the 13.6 divided by n squared. Okay, so I'm only focused on this term by itself. And then at the end, I'm going to add them up. This is negative, the other one is negative. So it's going to be, both of them are going to be shifted down. Make sense?
Yeah, makes sense.
Yeah. Okay, so because I'm concerned about the precision in here, because this is a fine structure. Fine structure means that these corrections are tiny, okay? So I'm only concerned with the coupling term in here due to the spin orbit coupling, okay? This is the term that has the alpha squared in it. So I'm only concerned with the alpha squared term. That's why I have 137 in here, 137 in here. This is what is really making everything small. It's that alpha squared, okay? Otherwise, this is 13.6 divided by 16. It's a decent number, okay? It's not big, but it's 13.6 times 5 divided by 64 is of the order of 1. Okay, but it's this term, the coupling term, is the one, the alpha, which is really the coupling term itself, is the one that is dictating. You have to understand something, that this formula is not an exact formula. This is an approximation. There are other terms involving alpha to the power 4, and other terms involving alpha to the power 6, and so on and so forth. So this is really a Taylor expansion. So this is the leading term due to the relativity corrections. So this is not the full picture. This is just the leading term, the correction. And as you can see, even the leading term is so tiny, okay? So the others are even tinier. That's the point in here. You're not noticeable at all. So this is good enough for our calculations, okay? So this is really the calculation. So all I did was at this point is found the shift from the value that I would have found if I did not include the coupling, the spin orbit coupling, okay, plus the corrections to it. That's all. That's the energy levels. So the energy levels that we saw in the hydrogen atom are not exact, so we shifted them a little, okay? But that's not the full question. The full question says in here, of course, there is another one going on for the n equals to 1, okay? And calculate the difference between the two. Oh, the difference between them is going to be 4 times as much, okay? So the difference now, to go back to your question earlier about why we were not bothered with this value, if I want to find the difference between those two values is going to cancel out. So if I want to find the difference between this one and this one, and use the full-fledged formula, then in this case, that term is existent in both of them, doesn't depend on J. So it's going to cancel out. So the only thing that I'm going to find is this difference. And the difference between these two values obviously is going to be 4 times the same thing, because I have 5 and I have in here 1 times the same factors in here of 64. So in this case, this will be just 4 times as much, so we can find the difference. Does this make sense, at least for this question?
Yes.
Okay, very good. So, and then find the difference in wavelength between a photon emitted in transition from state n equals to 2, l equals to 1, j equals to 3/2, to a state with n equals to 1, l equals to 0, and j equals to 1/2. So if you do the calculation, because there is another energy level that we have to find in here, and the energy level is for n equals to 1, l equals to 0, because we have to have a remember the selection rule still applied. Delta L needs to be at least plus or minus 1. So if we started from L equals to 0 in here, which is fine, L equals to 1, we can end up in L equals to 1. So this is allowed. Okay, so this is fine. So otherwise, if we started from, because n equals to 2 has another value, which is L equals to 0 also, that we didn't compute. Okay. But that from L equals to 0 to L equals to 0, that's not going to be allowed. So we cannot do that. We don't need to do that. I mean, it's, first of all, even if you calculate the difference in energies, it's not going to matter because it doesn't exist. So that's why the calculation for L equals to 0 in here is irrelevant. Okay, for n equals to 2. For n equals to 2, you have 2 values of L. You have 0 and 1. But since we're at the end concerned with the transition, transition can happen when delta L changes by either plus or minus 1. In other words, the photon that emerges from this emission can be spinning this way. I mean, it can has a polarization this way, polarized circularly this way, or polarized in the opposite direction. Okay, a left-handed or a right-handed polarization, doesn't matter. As long as it has an angular momentum, we're fine. Then we have conservation of angular momentum. Okay, so but when L is equal to 0, the photon that emerges will not have an angular momentum, which is a violation of conservation of angular momentum. Okay, from 0 to 0 doesn't exist. So that's what this means. Okay, for the selection rule. And j equals 1/2. Of course, when L is equal to 0, the only possible value for j is 1/2. Okay, because you're going to take the absolute value of 0 plus 1/2, and that is 1/2. So there is only one value in here. So for the other one, we're not too concerned about it. So we have 2 1/2. Okay. So it's going to be negative 13. No, not 2. 1. N equals to 1. I'm sorry. N equals to 1. Negative 13.6 divided by 1 squared times 1 plus alpha squared over 1 squared times 1 over 1/2 plus 1/2 minus 3/4. Let's look at this number in here, because that's going to determine the shift also in the n equals to 1 level. Okay, I have 1/2 plus 1/2, that's 1, minus 3/4, and that is equal to 1/4. So this is positive, times the negative, that 2 is shifted downward. Okay, so the energy level, which is negative 13.6, by the way, when you divide it by 1, it's just 1. When you shift it only by one value, and that value in this case is this whole term in here, which is negative 13.6 times alpha squared, which is 137.04 squared, and that factor of 1/4 that comes in here. So this is the shift in the energy level from that state. So now here is how the picture looks like. The n equals to 2 level, which was originally here, now has 2 values, either here or here. And the n equals to 1 level, so this is negative 13.6, and this is negative 4.2. Negative 3, not negative 3.4, I'm sorry, 3.4, okay, 3.4. Okay, so this is it sitting in here. I could have this transition, or I could have this transition. Okay, so those are the two possible transitions in here. In other words, the delta L, there is a lambda corresponding to this way shift, and there is a lambda corresponding to this shift. This is a higher energy, as you can clearly see from the graph, than this one. Because it's a higher energy, and because the energy is given by hc over lambda, that means lambda, the wavelength, is inversely proportional to the energy. That means the higher the energy, the shorter lambda is. So this is a shorter wavelength. And this is a longer wavelength because it's less energy. Let me remind you that this came from 3/2, and this is 1/2, and this is only 1/2. Okay, so the shift from the 2p 3/2 and the 2p 1/2 to, in this case, the 1s 1/2 has broadened. Okay, has broadened. Remember, this is the this is actually in the UV range. So this is not in the visible range because this is not the Balmer lines. This is another one. This is not the visible range. Anyway, the point being in here, I have there is a broadening on that line. It's not one line by itself. It's actually broadened by delta lambda, and delta lambda now. Look, the whole point that I was trying to argue earlier is that there is a very tiny shift in the energy. And this corresponds to a tiny shift in lambda also. And for that, I'm going to use differential formula in this case, d lambda, which is the derivative of lambda as a function of E times dE. Okay, and if I take the derivative in this case is going to give me d lambda, or delta lambda in this case, because that's what I want to find. Delta lambda is going to be the derivative of this function with respect to E is minus hc over E squared times delta E, the shift in energy. So the shift in energy is exactly what the question was asking earlier, that factor of 4 times this 13.6 divided by 64. Because remember, 4, this one minus the other value is going to give me a factor of 4. Don't be bothered with the negative sign. The only meaning for the negative sign in here in this case is that the function lambda as a function of E is inversely proportional to it. That means if you increase E, lambda decreases. That's all. So technically, since I'm just concerned with the shift, I can take it in absolute value in this case, which is everything is positive. So I'm going to take it in this form times delta E, where delta E now is going to be also taken in absolute value because we're concerned with the shifts only, meaning the difference only. Okay, so it's like when you calculate errors in your experiment, if you go up slightly or less slightly, it just contributes to the error, both of them. It doesn't mean that you're canceling the errors in this case. So the same thing in this case in here. So the negative sign has only meaning of the function, how the function lambda, the wavelength, depends on the energy, which is when you increase the energy, the wavelength decreases and vice versa. That's exactly what's going on in here. So the shift, the broadening, you're going to find one of them has moved. So this is the line. One of them has moved slightly, probably higher. No, both of them are going to be shifted. Okay. You know what? You're going to do this. Check exactly which one, where do they sit on the spectral line? But they shift, okay? And this shift, of course, is going to be a very small shift compared to the actual wave. In other words, if it was in the visible range, it's not going to change its color. If it was blue, it's going to stay blue. If it was red, it's going to be red, but slightly on one side, not exactly on where it was centered before. That's all. And you have to really have a fine measurement system to detect that shift also, okay? Anyway, so at this point, we're ready to do the calculation for delta lambda, and that's really the big deal in here. Okay, hc over E is exactly lambda, and because lambda itself is not changing, so lambda itself is just coming from the difference in energies in this case, which is a difference of 13.6 electron volt and 3.4. So E itself, you can take it as, so delta lambda is going to be the original lambda, which is really H, let me write it down, HC over E times delta E over E. So this value here is the one that corresponds to lambda naught, if you wish, the unshifted value, which is equal to H, which is a constant, times C, which is a constant, divided by the difference in energies between 13.6 and 3.4. Of course, it's in electron volts. You have to either write this value in electron volts so that you get lambda in meters, or you convert this one to joules and keep this one in joules times second. Okay, so you have to take care of units. Okay, once you find that, that is how the shift in lambda is equal to delta E over E, and delta E is this number, this value, minus this value. That's the shift in energy. I'm sorry, not this value. No. I gave you something completely nonsense. I'm sorry, guys. Okay. Yeah, that's the difference because at the end of the day, this stays the same. So it's this one minus this one. So this energy minus this energy. This is everything else is the same. This energy is the same. This between them. So when you subtract the two, this cancels anyway. And the 3.4 cancels from both terms in here, and the 13.6 cancels from both terms in here. So at the end of the day, it's going to be exactly this number times 4. 13.6 divided 64 divided by 137 times 4 in electron volts. Please do the example and go through the calculations, okay? And that gives you delta E divided by E, and E in this case is this difference between the two energies. 13.6 minus 3.4, which should be about 10.2 electron volts. So this is 10.2 electron volts. And this is 10.2 electron volts. And this is just constants. Make sure that if you write it in electron volt, each needs to be in electron volt. Okay, electron volt times second, of course. That's the units for the energy times second. C stays the same. C doesn't change. Okay. Makes sense, this example to you guys?
Yes.
Anybody else?
Yeah.
Okay, very good. So as long as you're taking care of the minutia, basically, of these calculations and not basically making your approximations too soon, you should be in good shape, okay? Because at the end, you can clearly see we need that delta E. And if we drop it during the middle stages, during these stages in here, and if we say, okay, here is the calculator it gave me, and I find delta E is equal to 0, then in this case, I would find no shift. Okay, so that's the reason behind that rationale in that, okay? Obviously, this value also is important too. You're gonna find the shift also, but as I was saying in here for a calculation of delta lambda, this at the end of the day will just drop out. But it's not going to drop out in the problem 53. It's going to be there, okay? So you have to pay attention to these things too. So it's not always what you see in one example works in another example. So you have to really do the actual calculations. In other words, you really have to. So problem 53. Let's take these ideas and apply them to problem 53. And I'm going to put a calculator in here and start doing things that way. So the hydrogen spectrum includes 4 visible lines. So now we're doing the visible lines, okay? So that means the final stage is n equals to 2. So we're going from some n bigger than 2 and ending at n equals to 2, okay? So that is really the whole point of it, okay? It has a wavelength of 434 nanometer that takes you from n equals to 2, this is 3, 4, 5. So this is 5 to 2. So this is wavelengths of 434 nanometers, okay? So this is your lambda naught that I was talking about earlier, okay? So if you did not use a high precision diffraction grating, you will get this wavelength and nobody will question you. So you're in good shape, okay? So this is that wavelength between n equals to 5 and n equals to 2. If we look closer, this line is broadened by fine structure due to spin orbit coupling and relativistic effects. How many different sets of L and J quantum numbers are there for n equals to 5 shell and for n equals to 2 shell? Let's start with the easy one, n equals to 2 shell, which we just did actually. Then in this case, L can be 0 or L equals to 1. Those are the two values of L. Now, remember, J is always equal to the absolute value of L plus 1/2. In this case, it's going to be, J is going to be exactly 1/2. And in J in here, it's going to have two potential values, either 1/2 when I take the minus sign, or 3/2, okay? So those are the two potential values that I will have. So for n equals to 2, then I have 3 potential different states, namely n equals to 2, I can have L equals to 0 and 1/2, and L equals to 2 also can have 1 and 1/2, an orbital angular momentum of 1, and J value, which is a coupling between the orbital angular momentum and the spin of 1/2, or an orbital angular momentum of 1 and a spin orbit basically connection and this interaction in this case of 3/2. What does this mean? It means that if the angular momentum is pointing somewhere upward, the spin is also somewhere upward, no, somewhere downward in here, and there is some cancellation so that at the end I will have a value of 1/2 for J. In here, both of them are pointing more or less in the same direction, okay? So they're not exactly parallel, but they are close enough from parallel so that their value is 3/2. And this is not exactly anti-parallel so that they cancel each other or something, but there is a small component in there of the coupling, okay? So that's what this really means, okay? But because we're going to get into more details later on, so this gets into a little bit of, so this is the values for n equals to 2. For n equals to 5, though, L can be 0, L can be 1, L can be 2, L can be 3, and L equals to 4. Those are the values of L. For each and every one of them, remember, J is still always equal to the absolute value of L plus or minus 1/2. This one will give me only 1/2 for J. This one will give me two potential values for J, namely 1 plus 1/2, which is 3/2, or 1 minus 1/2, which is 1/2. So I could have 1/2, or I could have 3/2. Same thing in here for 2. I have 2 minus 1/2, which is 3/2, or 2 plus 1/2, which is 5/2. Okay? So these are not the multiplying, just sitting next to one another. Okay? I probably should separate this by some commas or something. Anyway, the thing when here for 3, I have 3 minus 1/2, which is 5/2. And 3 plus 1/2, which is 7/2. You guys got the picture. The last one is going to be 4 minus 1/2, which is 7/2, and 9/2. So the energy level n equals to 5 is split into how many quantum states in here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9 quantum states. Okay, so it's the same level. Now it has shifted potentially by this many values. Okay. How many different energy levels are for n equals to 5 and for n equals to 2? Here is the tricky part though. The energy levels really do not depend on L. They depend only on J and N. Since N did not change in here, all I have to do is look at J. Remember the expression for the energy in here in general, the total energy to the spin orbit coupling is going to be equal to negative 13.60 electron volt divided by n squared. So this n now is 5 times open parenthesis 1 plus alpha squared divided by n squared times n over J plus 1/2 minus 3/4. This expression does not depend on L at all. It depends only on N and J. Since, let's look at the first one first. Since in this case, N equals to 2, L can have 1/2, J can have 1/2 or 3/2. Those are the only two values. So that's why, if you look at the example, the first example is split only in two, 1 and 2. So there are not 3 like this one suggests. You would think that there are 3 values, L equals to 0, 1/2, L equals to 1, 1/2, L equals to 1, 3/2. That is not true. You only have 2 energy levels for 2. And the same thing is true also for N equals to 5. N equals to 5, the 2 1/2 are the same value in here when you plug them into this expression. The 2 3/2 are the same value when you plug them into this expression. 2 5/2 are the same when you plug them into this expression. And the 2 7/2 also are the same thing, the only one that. So you have exactly 1, 2, 3, 4, and 5. So this is by itself, it's 5. So you have that level is split into 5 different energy levels. So basically, instead of sitting at negative 13.6 divided by 5 squared, then 5 squared is 25. So negative 13.6 divided by 25. Now it has shifted slightly by this much, by this energies in there. Make sense? This point?
Yes.
Okay, so for each of these values, what is the energy levels in electron volts? From the energy difference from negative 13.6 electron volt over N squared. So we're not again concerned about negative 13.6. We want to see the shift, that's all. So here is the first level. So this is N equals to 5. Obviously, the value that I probably should have written it in different colors in here because we're going to actually find the correct ones in here, okay? So this line, oops, did I erase something with that? Okay, that's fine. Let me change the color of the energy level, okay? So the energy level itself is negative 13.6 divided by 5 squared, and that is equal to, since I have the calculator in here, negative equals to, I have to have the equal sign, negative 13.6 divided by 25. It's negative 0.5440, okay? I don't know if Excel is giving me all of the sig figs or not. Yeah, that's correct, okay? So this up to 4 sig figs, electron volt, of course. But we're not concerned about that. We're concerned about the shift only. So we're concerned about the different shift values. So because this expression is lengthy, I have to do it 5 times. And because I don't want to do it 5 times, so I'm going to pull Excel actually and use it to find this value in there, okay? So call it lazy, call it whatever you like. It's actually smart to do it this way, okay? So we're going to stop sharing. And I'm going to share with you the Excel file that I have open in here. So let me take the formula first. We're only talking about the shift, okay? I'm not talking about anything else, okay? So I'm gonna put in here 5 and call this one N. I guess N is given. Okay, so let's put 5 in there and forget it for right now. And the different values for L, for J, I'm going to write them in here, okay? The J value is what? 0.5 and so on and so forth. So if I do equal to, Excel is really 1 over 2 is going to give me a 0.5. So instead of doing 1 over 2, I'm going to just write them explicitly. So 1.5, I could have done a series, but because there's few only, you guys know what I'm talking about. I could add it 1, 2, 3, 4. I think that's enough. I could have inserted a series in here and adding one where it's fill series, and we're gonna fill the column and add one, increments of one. Okay, I did not do it. Why? Series. Oh, I didn't find the terminating value. I'm sorry. Stop at value of, what is it? 9/2 is what? 5. Okay, I know it's 4.5. Oh, but I did it in the column. Sorry. Again, yeah, let's leave it on a column. That's fine. That's fine. But I should not have stopped at 5. Yeah, 5. 4.5 is 5, isn't it? It is 9.5. 9/2 is 4.5. Okay, so we're good. Okay, so we have the value of this one in here, but this one really should be a principal number. Should really change its name because I don't want it to change. This one, it's fine to change. Okay, so I'm trying just to set up Excel in here so that you guys are good at Excel, aren't you? All of you? Yes.
I'm a pro at it now.
Okay, very good. So I'm going to put equal to, again, I really don't want to do this thing in here. So 1/137.04. Okay, so this is my alpha term in here. Because what else do I need in here? So I'm set up everything. I set up the value of the n, I set up the value of alpha, and these are the different values of J. The only thing that I'm left with is 13.6, and probably I'm going to hard code that one. It's fine. Okay, so here is the formula though. It's equal to, this is the shift, not the whole thing. Okay, negative 13.6 divided by or times alpha squared, okay, times open parentheses principal, okay, so that value that I have in there, divided by open parentheses this value of J plus 0.5, okay, minus 3/4, which is 0.75, okay, and then close this parentheses in here. So this is the expression that I'm multiplying for and divided by the principal to the power 4. To the power 4, okay? Because I have n squared and n squared, that's to the power 4. So it's going to give me this value. Okay, here is what I need to be careful in here. So format cell, and I'm going to go to the scientific, what is the scientific representation, and I want to keep decimal points, 4 of them for right now. Okay, I know it's going to give me a precision of 5, but that's fine. Okay, and say okay. So that's exactly how it did it in here. So if I just copy this formula, it's going to give me the different values in here for the different ones. Okay, so this is, I probably should have labeled this ones. This is L equals to 0, J equals to 1/2. So we know what these things are. Okay, so this is the 1/2. This is the 3/2, and so on and so forth. So these are exactly how they are supposed to be. Obviously, the energy gets smaller and smaller as J increases. Okay, so in other words, we're not shifting much for those high values of J, as much as we are shifting for the low values of J. Okay, so this is the deepest one. So if I go back into my graph, this will be the closest one to, I mean, this will lead the smallest amount of energy, the longest wavelength. This one will lead to the highest amount of energy, meaning the shortest wavelength. So if I'm concerned with the broadening, This is what I'm going to be looking at, okay? Now, so this is for n equals to 5. We need to do the same thing for n equals to 2, but we have to be careful. For n equals to 2, the only two possible values are n equals to, L equals to 1 and 0, okay? So that means the only two values we should be reading off of this are this ones, or we can copy the whole thing in here, okay? Or we can do in here 0.5 and 1.5 and copy this formula and paste it in here. And why it did not give me an answer? Yeah, it gave me an answer. Okay, all I needed was okay, there is a problem in here. The formula did not shift. Did I make a mistake in here in the original expression? Okay. This is E1. That's fine. Yeah, that's correct. But for some reason, oh, n needs to change. You're right. So for this one, we need to change n. So we're going to put n equals to 2 in here, and or just rewrite the formula itself in here. I'm sorry about that. Okay. So this should not be the principal number, but should be 2. And this should not be the principal number, but should be 2. Everything else should be the same. Oops, 2. So this is better now. And we're gonna paste it in here, and we're in good shape. Make sense? The only thing is I need to make sure that my formula has the correct representation. And that's good. Make sense, this calculation so far?
Yep.
Okay, so it's basically straightforward in here, because let me go back to the energy levels in here just to make sure I didn't miss anything. There are 2 values, and the 2 values for J are 1/2 and 3/2. There are 5 values in here because there are 5 different quantum states in here, namely 0.5, 3/2, 1/2, 3/2, 5/2, 7/2, and 9/2. Okay, and each and every one of them has a different value. Okay, here is a question now. The deepest level from the n equals to 2 is this one. From the n equals to 1, it's this one. Okay. However, don't forget about delta L. Delta L can only be equal to plus or minus 1. So let me go back into the. Hopefully, you guys got these numbers in here, and at the end, we're going to need them. So because the next question has to do with the finding the photon. Because of delta L, we really have to be careful in here. Let me go back into the original OneNote. So we found 5 levels, okay? I'm going to write them down. So the deepest one is 1/2. So let's start with the closest one. So this is the one that corresponds to 9/2. And the value on this one is -2. So it's shifted from the 0.554, the 0.544 by this amount. 2.8967. No, that's it. 2.97. And even then, if we're going to find delta lambda, we have to be careful. Okay, we might retain more values. Okay, so it depends. Times 10 to the -7. So we're shifting this 5.4 10 to the -1 by this amount. Okay. So this corresponds to n equal to 9/2, meaning, and it's corresponding to only one value, which is L equals to 4. So this one is L equals to 4. Okay. The next one, that is 7/2, and this is L equals to 3. Okay. And for that, L equals to 3. or L equals to, what is it? Okay, L equals to, I'm sorry, L equals to 4 or L equals to 3. Both of them give you the same value. Okay, remember that there was two values that give you this one. So L equals to 3 or 4. Okay, so this one is shifted by an amount that is negative 5.7, which is slightly higher than this one in here, 93 times 10 to the negative 7. Again, electron volt. Everything is in EV. Okay, and the next one corresponds to 5/2, and this one is equal to negative 1.0621 times 10 to the negative 6 electron volt, and this corresponds to L either equal to 2 or 3. So this is important. Okay, and then the last one in here, or the last two in here, are equal to 3/2, and the biggest shift is actually for 1/2. Okay, so this one is equal to negative 2.0, twice as much as the first one, 277 times 10 to the negative 6 electron volts. And this one corresponds to L equals to 1 or 2. And this one is the last one in here, corresponds only to L equals to 1. Okay, and that value is negative 4.9244 times 10 to the negative 6 electron volt. Okay, this is the biggest shift in energy from the ground state. Now, if I look at the other one, namely the N equals to 2. So this is N equals to 2. Remember, it's negative 13.6 divided by 4, which is 2 squared. And that, I think we found it to be negative 3.4 electron volts. So this is the energy level that is corresponding to that one. And I'm going to change the value of N. So we have two values. The deepest one corresponds to N equals to, L equals to 1/2. And L equals to 1, which is J equal to 1/2. So we're going to find, first of all, the smallest shift. The smallest shift is N equals to, 3/2. That's J, the value of J. And that corresponds to negative 1.131 times 1032, actually. I need to do rounding correctly. 10 to the negative 5 electron volt. And this corresponds to L equals to 1. Okay, and the last one corresponds to L equals to 0. And that is a shift in energy by an amount of negative 5.657 or 78. You guys need to pay attention to, I'm being careless here, okay? So please make sure the rounding is correct, okay? Anyway, so here is where that thing can be tricky. Namely, delta L has to be at most equal to 1 or 0. From L equals to 0, I can only take this state or that state, okay? So I have two potential values in here for delta L. So let me draw it with a different color in here. So I have this transition that is possible. That corresponds to delta L equals to +1. Or as a matter of fact, this transition also, that corresponds to delta L equals to +1. Both of them are, because remember, this value can be also coming from L equals to 1, okay? Now for the L equals to 1, I cannot have from 1 to 1. This is not possible in here. But from 2 to 1, that is possible. So I could have this transition that is fine. Namely 2, and this is 1. Or I could have this 2 also to 1 also. This 2 to 1. But can we have from this one, from L equals to 1? No, so that's it. Did we forget the value in here for 0? Oh, 0 also. I'm sorry. This also, for 1/2, it's actually L equals to 0. Did I mess up in here, the numbers in here? Please pay attention to these things in here because I think I did. So this is L equals to 0, sorry. And this one is L equals to, what am I talking about? Where, how could I get to L equals to 1/2? Sorry. Okay. So this is 0 and 1. No, I'm sorry, this is 1 and 2, that's correct, 1 and 2. Okay, so there is a transition here that is prohibited that I accounted for. 1 and 2, 2 and 3, 3 and 4, and 4, that's correct. Okay, so there is no such a thing. So from here, from 0 to 0, this is not allowed. So there are only 3 transitions in here, it looks like at the end of the day, that are gonna be accounted for. Make sense? From 0 to 0, it's not possible because that makes delta L equals to 0, and that is not acceptable. That means the emerging photon will not have an angular momentum, and that's violation conservation of angular momentum. But from 1 to 0, that is fine. From 2 to 1, that is fine, which is this one, 2 to 1, that is fine. And from 2 to 1, that is also fine, because this also can come from L equals to 2. Makes sense how I got only 3 at the end of the day?
Yes.
Okay, here is the thing though. We need to find delta lambda, the broadening, meaning I have to find the actual difference in energies between this one. So earlier when we did the example, we really didn't care about this value in here because at the end it canceled out. No, it doesn't. Okay, so we really have to find the full-fledged value, which is 13.6 divided by P5 squared, added to it this difference value. Subtract from it the 3.4 minus this value in here, and find the energy in here. So I need to find E1, delta E1, that is the shift in energy between this and energy, and find delta E2 in here, and find delta E3 in here. The highest among all of these threes gives me the shortest wavelength. The smallest of these differences give me the longest wavelength. Okay, and then the difference between them is the broadening of the line. Sounds it's a good plan, guys?
Yep, sounds like a plan.
So I'm sorry that it took too long because I had to review first the example that we didn't do in class, but also the fact that we had to go through in-depth calculations to see the different shifts. And hopefully the tool from Excel should be helpful for you guys so that you can do these calculations a little faster and recognize the highest and the smallest. If in case you're given n equals to, I don't know, 7, for example, where the numbers become ridiculous, then at that point you have so many of them you have to consider, okay? And you try to find these things, the best bet in this case, first of all, use Excel all the time. It's a good tool, even for one calculation, okay? It's a good tool to use. And then the other thing also, you can rearrange those values. You can say, okay, give me the rank them from highest to lowest. When you do that, please keep in mind, let me share quickly this tip in here with you guys. When you do rearrange something, keep everything in order, okay? Don't just, so when you go to the sort function, what is the sort function? Data, sort. And then column G, for example, and from smallest to highest. If I do that, it did, yeah, it did not do that, did it? Why did not do that? Sort, column G, cell values, yep, from largest to smallest. That's weird. I thought this one is smaller than the other one. It doesn't matter, rearrange them for you, okay? I don't know why this is not working right now, honestly, but it should really have given you this values in here in the correct, because these are definitely smaller than these values. Anyway, if not, just basically pay attention to the differences between them, and that's it. And don't forget that these values are negative to begin with. Okay, so you're shifting the energy levels down. And the reason why I retain the negative sign is just to see that if one of them shifts upward, which is, I have never seen it, but if it does, then you need to be aware of it. You need to double check the calculations, okay? So this is the type of stuff that you could expect to be doing. By the way, problem 60 and other problems are similar. We still have about 15 minutes, so I'm going to introduce chapter 42 for you guys. And because these chapters are not part of this exam, so let me get going, and then maybe next Thursday when we meet, we're going to talk more specifically if you guys have any questions about the exam. And then we're going to continue the discussion on chapter 42. And then also we have an important lab that is also this week, assigned this week, okay? So let me get into my notes. Any questions before I delve into these things? And we're doing CH41, 42 now. No? So you'll probably put this book away. We don't need it. Okay. So basically, chapter 42, like I was saying earlier, we're not dealing with a single atoms anymore, but we're dealing with a combination of atoms. And molecules is a simple example of that when you have more than a single atom basically coming together. Like, for example, the example I have in mind is nitrogen or oxygen or hydrogen, okay? These are the ones that I'm really concerned with at this point are diatomic molecules, okay? Because if it gets a little bit more complicated and more involved, it becomes a little bit harder to visualize and do the calculations. So we're going to take simple cases, okay? One example that is probably could be also working carbon dioxide, which is you have a carbon sitting in the middle and here with a bond with the oxygen on one side and the other oxygen on the other side. So this is typical what you see in chemistry. So this is a triatomic molecule, basically you have 3 of them. But it has a simple enough geometry so that you can find, for example, its moment of inertia, and it's also maybe also you can approximate it to a harmonic oscillator, and where you can find the spring constant and how the molecules of the atoms of the oxygen and carbon dioxide start to vibrate and start to shake depending on how they are excited. Okay, you could use temperature if you like to excite them. Stuff that we have seen before in chapters 17 through 20. Okay, so this is things that we're going to be considering for the most part, diatomic molecules and how 2 atoms come together. So imagine with me, for the case of one of these molecules, take the hydrogen gas, for example, which is easy enough to work with. You have one s electron and another one s electron, and then coming together, okay? So the hydrogen atom, you have in here the nucleus, and you have in here the nucleus, which is positively charged, by the way. And you have a distribution in here with the wave function that is given by psi in this state, and another psi in this state. Both of them are symmetrical, by the way. S equal to correspond to L equals to 0 and L equals to 0. This is because N is equal to 1, and the only potential value for S is just in this case, if it's in ground state, is L equals to 0. So it's a symmetrical function. It has a spherical distribution around the nucleus. So when you bring them closer to one another, there will be the first thing that you will see is deformation of this, because you need psi squared, by the way, for the probability distribution of the electrons. So this probability distribution starts to deform, and the 2 atoms interact with one another. So there are different types of bonding that you can have in here, depending on how the electrons rearrange themselves to form this connection, okay? So the different bondings, of course, and you have seen them in chemistry, I'm sure. The first one is the ionic bonding. In the ionic bonding, in this case, there is an exchange of electrons. Okay. the typical example in this case is sodium and chloride. Sodium has in the outer shell has 1 electron. So what is the atomic number of sodium here? It's 11. And chlorine is 17. So really, this one needs just 1 electron to move to the argon basically structure, to group 0 basically. And this one has an extra electron, so if it loses this, it moves back to the neon and becomes also from group 0. So this is exactly what's going on in here. The energy it takes to extract an electron in here from sodium is not that high, relatively speaking, because of the affinity of the chlorine in this case to attract that same electron. So at the end, we will be left with 10 protons and 11 protons and 10 electrons, which gives me net charge of +1 electron. Okay. Whereas in this case, when we gain that electron, is going to be 18 electrons and 17 protons. Okay. So in this situation, I have a negative charge of negative E basically. So in other words, this is negative 1.602 times 10 to the negative 19 coulombs. And this is a positive 1.602 times 10 to the negative 19 coulombs. So those are two different ions sitting by themselves. One of them is positive and the other one is negative. Okay. They bond together because actually the energy, the affinity for the chlorine is not high enough to extract that electron in here. But the bonding between the two is actually the excess of energy to form, in this case, the molecule, which is NaCl. So if you can think of it as you have a positive charge and a negative charge, and they're attracted to one another, and they come to a certain equilibrium. Okay, so this is basically the ionic bonding. So this is an exchange of electrons. Okay. To do the calculations in here for the actual NaCl is a little bit more involved. And again, it involves basically, again, trying to solve Schrodinger's equation for it. And you come up with orbitals also that are similar in a sense to the SPDF orbitals. But in this case, I'm just giving you the details of the final picture. At the end, there are some calculations that we're going to take into account what is the different bonding energies and the different bonding energies in here, and just find the difference in energy, and it should be fine. So the other type of bonding actually is a covalent bonding. And in this case, like the example I was started with, the two atoms basically share the 2 electrons. So it's not like one of them takes and the other one gives. It's that there is a sharing of electrons in this case. Typically, this happens when the affinity of the 2 materials is similar for the electrons. They have the same basically energy it takes to extract the electron from both of them. This, of course, requires 13.6 electron volts to extract that electron. The other one also the same amount of energy. So in this case, what they do to stay in orbit in this case is they exchange. They don't exchange, but they share the electron. Remember, the spin of this electron could be anywhere between positive 1/2 or negative 1/2. The spin of the other electron could be positive 1/2 or negative 1/2. But because they're going to be sitting in the same quantum state for the molecule itself, the spins must rearrange themselves in such a way that if one of them is positive 1/2, the other one is negative 1/2. End of the story. So this is basically what happened in this bonding. So it's governed still by the Pauli principle in this case, but there is a sharing because the affinity of the 2 molecules is similar. Most of the bonding is of this type, though. It's not of the first type. Okay, most of the bonding of molecules is of the covalent bond, not of the ionic bond. So this is another way for molecules to form. Okay, and this is typical for a lot of these molecules that I was mentioning in the beginning. Okay. The other bonding that could happen is from dipolar interactions in here. For example, for the case of water molecule, there is a shift. I mean, there is a different affinity again between the for the hydrogen atom in here and the hydrogen atom, and the two electrons now sit together in here. So in this case, the sharing is close enough actually from the hydrogen, from the oxygen, because it has actually a higher number of protons to begin with, so it attracts more towards it than this one. So there is a net shift of charge in this case, not in exactly E, like in the case of the ionic bonding, but a small amount delta, which is a negative value, and a small amount delta, which is a positive value. So from a distance, this molecule looks like an electrical dipole. Okay, so this molecule looks like I have a negative delta sitting in here, and I have a positive delta in here, and this is the distance between them that you guys did in physics 1, physics 2, I should say, where the dipole moment, the dipole, what do you call it? The dipole, not the dipole moment. The dipole moment is for the other one, for the magnetic field. It characterizes by the distance 2a times delta, 2 delta a. Okay, where the distance to A is between the, I lost the word in here, but the point being in here, this is the characteristic of the of this dipole, and all of the interactions now are based on this properties. This is the water molecule, so from a distance you have a positive charge and a negative charge, not exactly E, but a fractional value of E, and now they can do what they can do in this case. They can actually bond with the next neighbor in this case. So I can bring another hydrogen in here and bring it on this side because it's positively charged next to it. It's going to be attracted to the negative charge. So some sort of a dipole-dipole interaction in this case to bring them closer. So in this case, it's called the van der Waals force between both of them. So this is another type of bonding. Okay. The last bonding, and that's going to be important for us, is the metallic bonding. And the metallic bonding is metallic bonding. And in this case, it's a sharing or communal sharing. And this is, we're going to discuss it later on, sharing of electrons. This is typically for solids, okay? So in this case, what have we have in here? We have a metal, like for example, iron itself, or any metal. So the iron in this case, the nucleus, and for the most part, all of the other inner electrons, they're tightly bound, and they cannot move. So the same thing for the next iron, and so on and so forth. But the electrons that are in the outer shell can move freely. Actually, they're very, very loosely connected to their host atoms. So when there's any thermal agitation, they get basically excited and they become free. So in this case, the number of electrons is exactly equal to the number of ions, in the sense that at the end, the total charge is equal to 0. But these electrons, they can move and they bond the entire structure together. Although not a single atom owns a single one of those electrons, but the whole thing is owned by the entire community of the atoms. So in a sense, it holds the whole thing together. So this is, we're going to discuss it later on in more detail when we talk about solids, okay? When we talk about solid state physics. So it's toward the end of the chapter, which is going to be the bulk of this discussion in this case, okay? So let me go back into the different spectra. How are we? Oh man, we still have 1 minute. Sorry about that, okay? So anyway, we're going to get into the details of this chapter. So what we're going to be doing in here is we're going to get into the spectrum of a molecule, which is important. That's how we're going to study its composition and all of that. So we're going to see 2 different kinds of spectra, the ones that are dealing with rotation. And that's why I took those simple atoms, because it's very easy to to find the moment of inertia for those molecules and find the different angular frequencies that go with it. And then when we do a spectral analysis, we will see that those spectral lines, they sit in the the microwave region. So we're going to find those values. And also, we do also the vibrational oscillations of this ones, and we model it, like I said in the beginning, with harmonic oscillators with the spring constants that we can measure. And then at the end, we're going to also find the different spectral lines using concept we learned from quantum mechanics. So after that, we're going to go back into the solids in this case and see that they have a bunch of atoms in here and they come together. Each and every one of them has its own wave function at the end, at the outer shell, basically. That's where the bonding happens. And that deforms the wave function. And the energy levels do not stay in their places because of the Pauli exclusion principle. They start to broaden, forming bands. And we'll be calculating those bands and calculating the difference and really getting the properties of metals, conductors basically, versus insulators versus semiconductors. And we'll finish it with studying the diode and transistors as part of examples of the semiconductors. We'll talk a little bit about superconductivity and we're done with this chapter. Sounds good, everybody?
See.
Okay, so I'm gonna stop the recording and I will see you guys on Thursday.